Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we are going to start with module 11. In module 11 we will be mostly discussing about source parameters and earthquake statistics. This is your lecture 1 where we will be discussing about earthquake magnitudes and movements. In the lecture today we will cover the concepts such as movement and magnitudes. In magnitude we will be discussing about the first scale, that is the Richter magnitude scale. Thereafter we will be discussing about body wave and surface wave magnitude, and then finally we will be talking about the advantages and the limitations of the local magnitude, body wave and the surface wave magnitude scales, followed by uncertainties in the magnitude estimation, and finally we will be discussing about moment magnitude, and then we will be having the summarized view of today's lecture. As far as the magnitude is concerned, just after having to locate the earthquakes, there was a need to quantify the size of earthquakes, and it is needed for both the scientific purposes and to discuss their effect on society. The first measure introduced was the magnitude, and that was based upon the amplitude of the resulting waves recording on a seismogram. Typically, the earthquake magnitude scale looks something like this, which is a logarithmic of amplitude divided by time period and has some factor which is depending upon the source depth and the epicentral distance, and there is this C, that is the regional scale factor. So the concept is that the wave amplitude reflects the earthquake size. So the magnitude scale that we are going to discuss about will highly be depending upon the amplitude that is coming in the seismogram, and then this will be corrected for the decrease with the distance due to the geometrical spreading and attenuation. And if you look at this scale, if you even increase the magnitude by 1 unit, then due to the logarithmic value at base 10, the amplitude of the earthquake will be increased by 10 units. So this is what it is written here: measured magnitude range more than 10 units, because the displacement measured by the seismometer span more than a factor of 10 to the power 10. So it tells us that the magnitude of the earthquake more than 10 is also possible, because if the displacement, that means this value here a by t, if it goes more than 10 to the power 10, then the magnitude will also go beyond the 10 units. Now look at this figure. It is a nomogram, and that is basically a Richter magnitude scale, and Richter magnitude scale is defined for the Southern California earthquakes and determined from the amplitude measured on a specific seismogram that is known as the Wood-Anderson seismograph. And there is an example earthquake given in terms of seismogram, and there are the P and S waves marked on it. So from the arrival times of P and S waves, we can easily compute the S minus P travel time difference between the arrival of shear and the compressional waves. And for this earthquake, this is around 24 seconds. And the largest amplitude of the body wave is for the shear wave here, that is around 23 millimeter. Now, if you look at this Richter magnitude scale carefully, then you will find there are 3 nomograms. One is for distance and the S minus P arrival times, and in the middle the magnitude scale is given, and on the right far there is amplitude in millimeter is given. So the concept is, you can mark the S minus P arrival time onto the leftmost nomogram here, that is around this point, and you can also locate the amplitude 23, that is 23 millimeter, that will come somewhere over here, and when you will join these 2 points together and wherever it will intersect on the magnitude scale, that will basically give you the magnitude of the earthquake. And the magnitude of the largest arrival, that is most oftenly for the S wave, is measured and corrected for the distance between the source and the receiver, given by the difference in the arrival time of the P and S waves. So this is the formula for the local magnitude scale, and it is log A plus 2.76 log of delta minus 2.45. And if we talk about the Richter magnitude scale that we just saw, it basically in the original form it is no longer is being used, it is upgraded. That is because most of the earthquakes do not occur in California, and the Wood Anderson seismograph are right now rare. And as far as if we talk about the advantages of having the local magnitude scale, then the local magnitude scales are sometimes still reported because many buildings that we have around us are having the resonance frequencies near to the 1 Hz, that is basically close to that of the Wood Anderson seismograph. So ML is often a good indication of the structural damage an earthquake can cause. So the takeaway is that the Richter magnitude scale in original form is no longer is being used because the original Richter magnitude scale is derived for the Southern Californian earthquake, and the earthquake can happen anywhere around the world. So this magnitude scale is no longer being used. Another drawback of this magnitude scale is that it is for a specific seismograph, that is the Wood Anderson seismograph, and having the Wood Anderson seismograph on these days is quite rare. And for global studies, if we want to find out the magnitudes, then the body wave magnitude and the surface wave magnitudes are preferred. Body wave magnitudes are written by small m in subscript B, and surface wave magnitude are represented by capital M in subscript S. And let's talk about the body wave magnitude scale first. So body wave magnitude MB is measured from the early portion of the body wave train. Usually the first 5 seconds of the wave train of the body waves are used to measure the body wave magnitude, and they are often of the period less than 3 seconds, usually about 1 second. So the body wave magnitude scale in empirical form can be represented by this particular expression: mb is equal to log at base 10 a by t plus q h comma delta, and this q is an empirical term here, and that depends upon the distance and the focal depth of the earthquake. And A is the ground motion amplitude in microns after you remove the effect of the seismometer. Generally, we consider first 5 seconds of the record, and that is for the period less than 3 seconds and usually about 1 second, and T the time period of the wave in seconds, and Q, as I told you previously, is an empirical term depending on the distance and the focal depth. MB is generally measured up to a distance of 100 degree, and if you going to use beyond 100 degree distance, then there will be effect of the diffraction around the core, and that will make our amplitude little complicated. So it is generally not preferred for the distances more than 100 degree. Now let's talk about the surface wave magnitude, that is represented by capital M in subscript S, is measured using the largest amplitude from 0 to the peak value of the surface waves. In general form, the surface wave expression looks something like this: ms is equal to log at base 10 a by t plus 1.66 log at base 10 delta plus 3.3. Here delta is the epicentral distance, a is the amplitude of the ground motion in microns after the effect of the seismometer is removed, and this t is the time period in seconds, and the delta, as I told you, is distance in degrees. And most oftenly we do consider the period of the Rayleigh wave, that is should be around 20 seconds or you can say the periods of 20 seconds of the relay waves generally has the largest amplitude. So this particular formula will reduce to this particular form, and you can see this is written for the wave of relay wave, that is for 20-second periods. So ms is equal to log at base 10 a20. A20 is the amplitude of the 20-second period relay wave, plus 1.66 log at base 10 delta. Delta is the epicenter distance, plus 2.0. So there are certain advantages and certain limitations of the magnitude scales that we discussed so far. So we have discussed about the Richter magnitude scale, local magnitude scale, body wave magnitude scale, and the surface wave magnitude scale. There are certain advantages. Those advantages are like they are directly measured from seismogram without sophisticated signal processing. As you can see, when we are discussing about these three magnitude scales, then we have seen these were depending upon the amplitude and the time period mostly, and we were not having to do any sophisticated signal processing. So these are directly measured from a seismogram. They yield unit of order 1 which are intuitively attractive. That means like when you go somewhere and tell somebody, ask you what is the magnitude of the earthquake, then you can generally say magnitude is 1, 2, 3 or 4 or 5, whatever. That these numbers are intuitively attractive. It is not something like you are saying 10 to the power 10 magnitude or 10 to the power 11 or something. Those are a little complicated and doesn't look so attractive. So these numbers of the magnitude from 1 to 10 or more than 10 are intuitively attractive. Magnitude 5 earthquakes are known to be moderate earthquake. Magnitude 6 are strong, 7 are major, and 8 are great, which means that the magnitude of 5 earthquakes are called as moderate earthquake, magnitude 6 is known as strong earthquake, and 7 is major, and more than 8 magnitude earthquakes are generally known as great earthquakes. There are certain limitations to the magnitude scales. The limitations are, the first and foremost is they are totally empirical and they do not have any direct connection to the physics of the earthquake, which means that the magnitude scales are totally empirical and they are not derived from certain mathematical expressions, and we just have their certain values plotted on a piece of graph of paper, and then we just draw certain lines or the best fitting curves to basically find out the formula. Those are empirical and thus have no direct connection to the physics of the earthquake. That means we are not involving any geometrical parameter or the geological parameter of the fault involved in the occurrence of the particular earthquake. And magnitude equations, if you look at these magnitude equations, certain and or this one or the one that we just saw for the body wave magnitude scale, these equations are dimensionally incorrect because we are taking the logarithm of a by t, that is not a dimensionless quantity, and logarithm can be taken only for the dimensionless quantity. So this is what it is written: magnitude equations are dimensionally incorrect. Logarithm can be taken for dimensionless quantities. A second difficulty is with the numbers that emerge. Magnitude estimates vary noticeably with azimuth due to the amplitude radiation pattern, although this difficulty can be reduced by averaging result. So for example, if suppose there is an earthquake here and there is a certain station which is recording your seismogram, so for this station the rays that are coming to these stations will be experiencing certain geological features and their radiation pattern may be different from the station somewhere here that is basically located in a different direction or different azimuth direction. So this is what it is written, because there will be a difference in the seismogram in both of them, so there will be the difference in the amplitude as well, and this will basically have certain effect on the magnitude values that we will derive using the formulas that we just saw. So magnitude estimates vary noticeably with azimuth due to the amplitude radiation pattern, although this difficulty can be reduced by averaging result. So in that case, when you have certain variations in the magnitudes, then for different stations, then you just can take the average so that you can come out of that difficulty. The different magnitude scales yield different values. So if you calculate the MB value, MS value, or the ML value, all will come out to be more or less different. So this is also one of the problem. Body and the surface wave magnitude do not correctly reflect the size of the large earthquake. So this is the problem of magnitude saturation, which means that after a certain magnitude, the body wave and surface wave magnitude gets saturated. That means they do not show the correct magnitude value of the large earthquakes. So after a certain point, for example, for the body wave magnitude scale, the above, if the earthquake is happening more than 6.2 magnitude, then it will always show the magnitude of 6.2 for even a large magnitude earthquake. If you consider a surface wave magnitude scale above 8.3, it gets saturated. So this is what it is written: magnitude saturation is a general phenomena for body wave magnitude above about 6.2 and the surface wave magnitude above about 8.3. So if a large magnitude earthquake, let's suppose 8.6 magnitude earthquake is happening in an area, and you are going to calculate body wave magnitude for this particular earthquake, then the earthquake, since we know the body wave magnitude gets saturated at 6.2, so it will still show you the value 6.2, although the magnitude of the earthquake actually is 8.6. For the surface wave magnitude scale, the value will saturate at around 8.3. So for this same earthquake, it will show 8.3. So these two values, 6.2 and 8.3, are the saturation magnitude points for the body wave magnitude scale and the surface wave magnitude scale. Larger fault dimension give rise to greater slip. So the combined effect of larger fault area and more slip cause the largest earthquake to occur at subduction zone rather than transform faults. So this is just an information. So larger fault basically gives rise to the greater slip, and they have larger rupture area. So so more obviously the larger movement are associated with it, and larger energy will be released in case of these earthquakes. And these earthquakes generally happen at the subduction zones rather than on the transform plate boundaries. So this is a table that we took from Stein and Weiss session, and this table best present or give you the introduction about the magnitude saturation. For example, if you look at these earthquakes, these are 6 different earthquakes. These are given like one is the Turkey 1966 earthquake, another is San Francisco Fernando 1971 earthquake, Loma Prieta 1989 earthquake, San Francisco 1906 earthquake, and Alaska 1964 earthquake, Chile 1960 earthquake. And their associated body wave magnitudes are also given into the second column, and their surface wave magnitude are given into the third column, and the rupture area is given into this column, and the slip is given into this particular column, and the movement that it releases associated with these earthquakes are given in this particular column. And finally we will talk about the movement magnitude scale. So now let's concentrate the values of the body wave magnitude and the surface wave magnitude. And now look at the movement. So the Turkey earthquake's movement is this one, which is quite smaller than the San Fernando earthquake. And likewise, San Fernando's movement is smaller than the Loma Prieta, and then Loma Prieta's movement is smaller than San Francisco, and San Francisco's movement is smaller than the Alaska earthquake, and Alaska's earthquake's movement is smaller than the Chile earthquake. So the movements are in increasing order here. So movement are increasing from Turkey earthquake to the Chile earthquake from top to bottom. And similarly, if you look at their average slip or dislocation, then they are also increasing from top to bottom, and the fault area is also increasing from top to bottom. So you can easily understand the Chile earthquake is having the largest movement, and that is followed by Alaska, and then San Francisco, then Loma Prieta, and the smallest one is the Turkey earthquake. So if you look at the body wave magnitude of the Turkey earthquake, that is 5.4, and then San Fernando has 6.2, Loma Prieta has 6.2, and the Alaska earthquake is also having the 6.2. So now you could easily understand the problem here. Even the earthquake size is much bigger as you go from top to bottom, but the body wave magnitude is still stagnant, that is around 6.2. That means at its saturation point it is getting the stagnant values. After 5.4 it goes 6.2, but thereafter it remains as 6.2. Similar problem occurs with the surface wave magnitude, and you can see the surface wave magnitude after 8.4 or 8.3 it gets stagnant. It doesn't basically give you the greater values for the larger magnitude earthquake. So this is basically happening because of the saturation. We will soon understand in the next lecture that how the magnitude saturation occurs and what are the possible regions because of which body wave and the surface wave magnitude scale saturates. So given these problems, there was a need to devise a magnitude scale which can better represent the correct values of the earthquake magnitudes. So the most updated scale was given, and it was named as the moment magnitude scale, and it is represented as M in subscript W, and you can see their values for these different earthquakes. So if you go from top to bottom, their values are increasing and these are not saturating. So these are basically representing the correct magnitude of these earthquakes. 5.9 for the Truckee, San Fernando 6.7, Loma Prieta 6.9, San Francisco 7.8, Alaska 9.1, Chile earthquake 9.5. So this is what it is written here. As shown, MB and MS differ significantly. The earthquakes with movements greater than that of the San Fernando earthquake all have body wave magnitude 6.2, even as the movement increases by a factor of 20,000. So even the movement is increasing like by a factor of 20,000. That is quite a large value, but the value of MB is still 6.2. That is happening because of the magnitude saturation. Similarly, the earthquake larger than San Francisco earthquake has MS surface wave magnitude about 8.3, even as the magnitude movement increases by a factor of 400. So this clearly depicts the problem what we have in terms of magnitude saturation. So there are considerable. So basically, now let's talk about the uncertainties in the magnitude calculations. There are considerable uncertainties due to the various causes. There are uncertainties due to the Earth's variability and deviations from the mathematical simplifications used. For example, even with high quality modern data, seismic movement estimates for the Loma Prieta earthquake vary by about 25% and MS values vary by about 0.2 units. The estimation techniques vary. The actual approaches used to compute magnitudes have changed with time. So if you give, for example, like before 1964 Alaska earthquake, the body wave magnitude values were not used to be reported. So this is basically a problem because of the use of the different techniques used. So uncertainties for the historical earthquakes are especially large. Different techniques for body wave, surface wave, geodesy, geology can yield different estimates. The fault dimensions and the dislocations are basically the average values that we have shown you in the previous table are that are for the quantities that can vary significantly along the fault. So for that purpose, if you want to estimate the dislocation and the dimension of the fault, you need to use you basically need to be confirmed about those are basically measured up to very little amount of uncertainties. So and if there is a significant amount of uncertainties, then the magnitude values will also be uncertain. We have seen that the amplitudes depend on the scalar movement, the azimuth of a seismometer relative to the fault geometry, the distance from the source, and the source depth. Now that we have talked about the moment magnitude scale, that is considered to be the most updated and the better magnitude scale in comparison to the local magnitude body wave and the surface wave magnitude scale, especially in the case of larger magnitude earthquakes. So a magnitude based on seismic movement is referred as moment magnitude, and the formula is given by this: log of m naught divided by 1.5 minus 10.73. Here m naught is the seismic movement in dyne centimeter, and it gives a magnitude directly tied to earthquake source processes that does not saturate. So if you look at the value m naught, that is basically mu ds, and it basically, this value is basically depending upon the fault parameters such as the shear modulus of the rocks around the fault, and this mu is the shear modulus, and d is the slip along the fault, and s is the rupture area. So it gives a magnitude directly tied to the earthquake source processes that does not saturate. Moreover, it preserves the simplicity of the magnitude scale by giving values of order 1 compatible with other magnitude scales. MW is comparable to MS until MS saturates at about 8.2 but then increases. Estimation of M naught, and therefore we can find out the moment magnitude, requires more analysis of the seismogram than for MB and MS. So it is little bit difficult to calculate because it requires more analysis of the seismogram to find out the various other parameter in order to calculate the moment magnitude of an earthquake. The summary of today's lecture goes like this. The general form of the earthquake magnitude is something like this, which is basically m is equal to log at base 10 a by t plus f h comma delta plus c. So h is the hypocentral depth, delta is the epicentral distance, and c is the regional scale factor. So f is also can be called as f is the correction for the value variation of the amplitude with the earthquake's depth h. Richter scale magnitude is ml is equal to log a plus 2.76 log delta minus 2.48. Body wave magnitude mb is log at base 10 a by t plus q h comma delta. So body wave magnitude scale also depends upon the regional factors and also the seismometer that is used to calculate the body wave magnitude. And as I told you, for the Richter scale magnitude, that was in the original form was derived for the Californian earthquakes, and it is for a specific seismograph, that is Wood-Anderson seismograph. Surface wave magnitude, that is ms log 10 a by t plus 1.66 log 10 delta plus 3.3, where a is the largest amplitude of the surface wave, which is generally for the Rayleigh wave, and if we go more specifically, in the Rayleigh wave at around 20-second period has the highest amplitude, so it can be written in the another form as well. Body and the surface wave magnitudes do not correctly reflect the size of large earthquakes and saturate about 6.2 and the 8.3 respectively. There are uncertainties in magnitude estimation due to Earth's variability and deviations from the mathematical simplifications used. Different techniques, body waves, surface waves, geodesy, geology, can yield different estimates. Moment magnitude scale is given by this particular expression. MW is equal to log of m naught by 1.5 minus 10.73. It gives a magnitude directly tied to earthquake source processes that does not saturate. So this is the lecture today, and these are the references. And in the next lecture, we will talk about the source spectra, and that is all. Thank you so much. Bye bye.